So, we are back again, but this is the last week, good news I guess, last week of the course, but we are going to learn some of the very important aspects of calculus. One which is called the infinite series, which we will have 3 classes followed by multiple integrals. So, we will start with infinite series. So, infinite series is required at many places where theoretically you can think of everything been happening in infinite up to infinite time. So, let me write down what is an infinite series, but I am going to just now talk about infinite series of positive terms. Infinite series of positive terms. So, it is written like so it just goes on, it never stops. So, this can be written in a shortcut way as follows: summation a n n starts from 1 and goes up to infinity. The symbol infinity does not mean some number, of course infinity is not a number, it is a symbolism which says that the sum does not stop, does not end, it is not a finite sum, that is all. Now, is there any meaning to the sum of the infinite series? Sum of the series. How do I even talk about the sum of the series? Okay. Now, let us note something. How do I actually approximate this sum? If I take just A1, then it is extremely crude approximation of the whole sum, because there is positive term. So, the whole term, if there is something like a sum, it must be bigger than all A1, then I put A1 plus A2, slightly better approximation, A1 plus A2 plus A3, slightly better approximation. So, essentially we are creating an increasing sequence. So, I will take a say S1 is equal to A1, S2 is equal to A1 and Sn An and goes on. So, Sn, this term, so I have formed a sequence. So, this is called a sequence of partial sums. So, if I look at this series, because these are positive terms, S2 is bigger than S1, S1 is bigger than S2, S3 is bigger than S2 and so on and so forth. So, basically it is like this: S1 is smaller than S2, so basically what is happening, Sn is smaller than Sn plus 1. So, it is an increasing series or non decreasing rather I should say, but actually it is a strictly increasing series, because if these are all positive terms then we are strictly increasing. Okay, just so now if this series is bounded above, if Sn is bounded above, then Sn converges to L is equal to supremum of the sequence Sn. So, what we were telling is that now if Sn goes to L, where L should be the supremum, and Sn will go to L because if Sn is bounded above, if Sn is bounded above, then we define this L as the sum of the series. Essentially some people want to call it a limiting sum also, does not matter, it is a limiting sum if you say in some sense, but this is the sum of the series. This is what is defined as the sum of the series, and we have to keep that in mind, where we have to be very careful about that. So, when there is a sum or the sequence of partial sums converge, of course, if the sequence of partial sums are bounded above, they will converge. So, if the and if this whole thing converges, then the sequence of partial sum must be bounded above. The sequence of if the sequence of partial sum converges, and if there is a sum of the series, then we say that the series converges. If Sn converges, we say that now it is very important to know how do I test whether a sequence, you know, every time you are not going to write down partial sums, right. So, if you are not going to write down the sum of take the partial sums and then try to find the convergence, is always not a good idea. There should be some easy way to figure out whether a sequence is convergent or divergent. One of the, so if the sequence does not converge, means either Sn is oscillating or Sn is going to infinity. In both cases we said that the sequence when the sum n does not converge, this does not have a sum or it diverges. So, it is important to now understand that there must be some ways to easily determine whether this sum n has a this summation n has a sum or not, or whether it converges or not. So, first one of the easiest test is called the comparison test. This comparison test only is working for series of positive terms, it cannot work for other things, or series of non-negative terms if you want to say. So, if for some n naught element of n we have a n less than equal to b n for all n bigger than equal to n naught, and summation b n converges, then summation a n converges. So, it does not matter if you have left out finite number of terms, if the remaining part converges, you can add the sum of the finite number of terms and you can have the total sum. Now, for example, consider this famous geometric series. Geometric series is something which you have already seen in high school. So, you can understand that Sn here must be less than 2, it does not matter, Sn should be always strictly less than 2 for all n. So, here Sn is always less than 2. So, you see immediately you see in this very simple case Sn, the sequence is bounded above, and so you can immediately say it converges. Of course, I leave it to you to decide that whether you, but this, for example, this one can be used as a sequence Bn to show something else is convergent. A second one is the following: if same thing, if for some n naught element of n we have a n greater than equal to b n for all n bigger than n naught, and summation b n diverges, then so does a n. See, we will now give a proof, we will use this, for example, we will use this idea to prove that if I will show, we will show that the harmonic series, which is consisting of the following terms 1 plus half plus 1/3 plus 1/4. There is a sequence 1 by n, series 1 by n. Now, we will use this comparison test, the second thing, to show that this actually diverges. See, what we can do is the following: we simply have to regroup this as follows: 1 plus half plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. So, you group up to 4, and n group here is up to 2 cube, here is 2 to the power 1, here the n group is up to 2 square, the n group is up to 2 cube, then n group is up to 2 to the power 4, that is 1 by 9 plus 1 by 10 plus. So, if you look at this, what does this become? So, this is become bigger than 1 plus half plus, you see 1/3 is bigger than 1/4. So, it is 1/4 plus 1/4 half. So, 1/5 is bigger than 1/8, 1/6 is bigger than 1/8, 1/7 is bigger than 1/8, this is 1/8. So, 4 times 1/8 is again half, this whole thing is greater than half, and similarly this is also bigger than half. So, this sequence 1 plus half plus half plus half plus half, this sequence diverges because the sum of partial sums is not bounded above, as a result of which we have a divergent series which is Bn here and my series was An here. You see that from this term there is a strict, this Bn is strictly less than the terms, these terms. So, basically immediately you see I have a sequence Bn and this Bn is converging. So, by this comparison methodology, so I basically regrouped, basically I have written, okay, instead of writing this sequence I am writing this sequence, I am writing this sum. So, I am telling that now what I am telling that this is the sequence. Now 1, the next sequence is, next term is, this is a series. So, first is term is 1, then the term is half, then term is 1/3 plus 1/4 this. So, each term, so this is one term, this is one term, this is one term of the rearranged series. Here rearrangement does not make a difference because these are all positive terms. So, here you see this term is bigger than half, this term is bigger than half, this term is bigger than half, so and so you have a sequence, and which is showing that this sequence is convergent or divergent, and this actually should be equal to this sequence. So, this sequence itself is also divergent. So, that is a little application of those ideas. There is something called integral test, which I do not want to explain to you because that would get you into some sort of more detailed things. There are several comparison tests which comes, one is called the limit comparison test. So, again it is only for sequence of a series of partial terms. If you have limit of n by Bn equal to C, n tends to infinity and C is strictly bigger than 0, then summation An and summation Bn converge and diverge together. Number 2, if limit n tends to infinity, n by Bn is equal to 0, and if summation Bn converges, then summation An converges. So, you can use the limit comparison test. right. Given a series, you can construct another series Bn and do the ratios An by Bn, right. If limit An by Bn then tends to infinity is equal to plus infinity, then if summation Bn diverges, then summation An also diverges. Now let us take an example. The example is like this, that you are considering the following series. So, each term, so if I put n equal to 1, it is 3 by 4, then the second term is 5 by 9 and so on and so forth. So, it is 3 by 4th plus 5 by 9 plus 7 by 16 plus. It does not seem on the very look of it that it might converge. So, let us, if I have having, by looking at it, if I am having some doubt, then I can easily consider this test, the try out the limit comparison test. So, what should be the, let me take Bn. So, if An is equal to 2n plus 1 by n square plus 2n plus 1, let me, because I want to check out divergence, because it looks like that it will just go up, blow up, then let me take Bn is equal to 1 by n. So, Bn is actually summation Bn is the harmonic series which we have just saw to be divergent. So, then what happens? Because what happens, you see that if you have, why I am suspecting this, just observe the following. For n very large, n square will dominate 2n plus 1. So, it is something like 2n by n square. So, it is almost like this. So, because of this you have a suspicion that it might converge. So, now let us do this An by Bn. 1 by n. An is 1 by n. So, n will go to the top. So, it will become 2 n square plus n by n square plus 2 n plus 1. So, you divide by n, here you divide by n. So, it will become 1 by n, here it will become, so you divide by n, divide by n square, then it will become 1 by n, then this, limit n tends to infinity, limit n tends to infinity, then it will become 1 plus 2 by n plus 1 by n square. So, the limit actually gives me 2. So, the limit is C, which is strictly bigger than 0. So, which means An and Bn both diverge and converge together, but summation Bn already diverges. So, we can now conclude that An diverges. So, we end the very simple test procedures here. We will come to our other test, how to do some important tests like the ratio test and the root test in the next lecture. So, we will talk about root test and ratio test in the next lecture, give you some idea of a series which is not formed of just positive terms as a plus minus alternating sign. That is very basic idea we will give, and then in the last one we will talk about power series, and largely the power series generated by the Taylor series rather the Maclaurin series. Thank you very much.